In the number of islands problem, you are given a map represented as a two-dimensional grid. Every cell in the grid is either a piece of land represented by a 1 or water represented by a 0. You are asked, given such a map, to find out how many islands are formed. An island is formed by adjacent lands connected either horizontally or vertically. In our example, there are 4 different islands. If some islands intersect only diagonally, they do not form a bigger island, but are treated as separate islands. So how can we determine how many islands are there? Since we are working with a grid, we can quickly get its dimensions and then use 2 loops to go through every cell it has. And whenever we encounter a 1, whenever we encounter a piece of land, we stop there and we look for the entire island that can be formed from that position. And what do we do with the island once we discover it in its entirety? Well, we sink it. That's right, down it goes, straight to the ocean floor. We should also increase a counter since we discovered an island. Once this is done, we continue iterating through the grid from where we left off. What happens when we find the next piece of land? Well, again, we pause our grid iteration to scan for the entire island that can be formed. And once we discover the entire island, you guessed it right, we sink it. Then we resume our grid iteration. The next piece of land we discover is itself an island. What do we do when we find an island? We sink it. And we repeat this process till we finish iterating through our grid. Now, there is one question left we have not answered. How exactly do we discover an entire island starting from a piece of land? What type of problem is that where we are asked to discover all the connected nodes that have a specific property? And the answer is, it's a graph problem. We can treat our grid as an undirected graph where each cell is a node. When we are asked to traverse an undirected graph, we have 2 main approaches, either a breadth-first search traversal or a depth-first search traversal. We'll take a look at how we can implement both. Let's start with the depth-first search, since it's usually more intuitive and easier to implement. First thing we do when we discover a piece of land is, well, sink it. Then we want to repeat the process with all its neighbors and its neighbors' neighbors. Knowing that we can go only up or down, left or right, we can represent this with 4 recursive calls to this method. Let's run this. And rather than going step by step through the recursive calls, let's imagine for a moment how all the recursive calls would unfold. And it doesn't take much time to notice that it's literally a mess. Our recursive calls grow exponentially, never stop, and quickly get out of control. Instead of only going through land tiles, they also continue expanding once they reach the water tiles, go through other islands, and not only that, they even go beyond the boundaries of our grid. We need to set some limits on where our recursive calls can go. First, let's make sure they stay within the boundaries of our grid. Then, we want to stop them from expanding once they reach the water tiles. Now, those zones are off limits. Those limits we've just set are called the base cases. Base cases act like security checkpoints. The recursion is allowed to arrive on them, and then the checks decide whether the calls should continue or be turned back immediately. Now our recursive calls can help us uncover the entire island. As we've just seen, whenever you approach a recursive problem, it's helpful to build some intuition for how the recursive calls unfold. But in practice, they won't run all at the same time. The path the recursive calls follow is that of a depth-first search traversal. The recursive calls go as deeply as possible, trying to build a solution, and when they reach the base cases, they backtrack and look for other possible paths to explore. One final thing we need to do for our solution to be complete is to check for some edge cases. Let's see how we can switch our depth-first search traversal to a breadth-first search traversal. So, what is the idea of breadth-first search? We start from an initial piece of land, we sink it, and we look at its neighbors that are land. Now, with those pieces of land, we sink them and look at their neighbors that are land. And now, with those pieces of land, we sink them and look at their neighbors that are land. And so on. You can see that it's quite close to the intuitive version we talked about when we tried to figure out depth-first search. Now, in our code, we start by sinking the initial piece of land and add its position in a queue. Now, the whole idea of breadth-first search is that as long as this queue is not empty, so as long long as there are elements in the queue, we pop an element out of it, we look at its 4 neighbors, and those that are within our grid and our land, we sync them and add their positions in the queue. We repeat this process, popping one element out of the queue and adding its neighbors till the queue is empty, and then we will have discovered our island. And that's it for this video. If you like the content, hit the like and subscribe buttons, as this helps the channel a lot, and hope to see you in the next one.